Thermochemistry sounds like a very intimidating word. What you really need to understand is this is stoichiometry. This is what we just covered. We're just factoring energy, which in this case, we're basically dealing with heat, which is one form of energy. What you need to remember are the steps for stoichiometry with a few minor modifications for energy. So you're going to write and balance an equation. You'll include energy where it might be needed. You're going to convert units into moles. That's what we've always been doing. You're going to find the mole ratio between reactants and products. Energy is counted as part of a mole ratio. You're going to cross multiply, canceling relevant quantities. That's what we've been doing already. Converting moles to desired units. Now, in this case, we could be converting things into kilojoules or kilocals. If you go on to AP Chem, be expecting to have to do a lot of kilojoule, joule, calorie, kilocalorie, watts, all sorts of conversions of energy, but it's basically just using your regular conversions that we've been doing since September, really. Units for heat, as I just mentioned, we have the little c calorie, which is the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Also remember that 1 gram is 1 milliliter. That's something important to remember, 1 gram per milliliter. So if you have 1 liter of water, that's basically 1 kilogram of water. 1 kilocalorie is 1,000 of the little c calories. These are the calories we find in food. So you may realize that food has a lot of calories in it, a lot of little c calories. The average human should be consuming like 2,000 calories a day. So that's 2 million of the little c calories. That's a lot of energy. But of course, a lot of that is basically going to maintain our bodies, keep our bodies warm, and a lot of it also goes to our brain because our brain's a huge energy hog, but it also allows us to do some pretty amazing things. The SI unit for energy is the joule, and that is the last name of the scientist who contributed a lot to our study of energy and our understanding of energy. The conversions, 4.184 joules is 1 little c calorie, and then 1 big c calorie is 4.184 kilojoules. In most of my calculations, I chop off the 4 at the end. It's just 4.18. Some sources will tell you it's 4.184. Some will tell you it's 4.182. Some will tell you it's 4.187. So in order to avoid all of that controversy, most of my calculations, I'm going to cut off that last number. 4.18 will give us good enough numbers that if it were in a multiple choice question, you'd be able to get the proper answer, which if you remember, our final is basically multiple choice. We remember with water has extremely high specific heat. One of the higher specific heats of just about any substance, at least commonly available substances. Metals, of course, have very low specific heats, which means it only takes a small amount of energy to take 1 gram of any metal and warm it up. We see this like on a hot day. If a sun's shining on a car and a sun's shining on a puddle of water, of course the car's metal hood will get much hotter, and that's because the same energy input will raise the temperature of the metal a lot more. You remember we dealt with calorimetry at the very beginning of the year with heat, specific heat. Q equals mc delta T. That's just a reminder that we've been here before and we've definitely done this before. Our food is measured in something called a bomb calorimeter, which will allow our food to be heated. What you do is you dehydrate food, a sample of food, you burn it, you determine how much energy went in to get the ignition started, you subtract out the energy that's radiated into the water from burning our food, and we are able to determine how much energy is actually in food. This is a really practical use for a specific heat problem, as we will be looking at it a little bit later in more detail. So, we're talking about heat. Heat, we're really measuring a change in heat. Every substance has a heat content at a given temperature and pressure. but it is not necessarily dependent on a specific temperature. So we can't really say how much heat is present until we see the change from reactants to products. That is how we determine this delta H value, which if we start with a certain set of reactants which have a certain amount of heat or a certain heat content, and then we see what the products end up with, we're able to see how much the heat changes. That's our delta H. In an exothermic reaction, heat is released into the system, therefore temperature goes up. We're not literally dealing with negative energy here. That is something completely different in the realm of physics. It's very cool stuff. Look up the Alcubierre drive if you want to look up something more about negative energy. But in this case, we represent delta H as a negative when positive heat is treated as a product. Heat is coming out of the reaction so that the reactants end up having less, the products have less energy than the reactants. If we go to a positive, then we're putting energy into the reaction. We're treating energy as a reactant, and the products have more energy than the reactants. In an endothermic reaction, we therefore have temperature going down. Heat is being absorbed by the system. So in an exothermic process, products have lower energy than the reactants. Therefore, energy is released into the system. As I said before, the negative sign does not mean negative energy. We're not talking about negative energy. When we put this number into our chemical equation, it is a positive number. It just depends on whether we put it on the left side. If it's a positive, we put it in with the reactants. If it's a negative, we put it on the right side with the products. This is a nice example of an exothermic reaction. Carbon and oxygen both have a certain heat content. Carbon dioxide has a different heat content. So heat is given off in this reaction. In an endothermic process, products are higher in energy than the reactants. Energy is absorbed by the reaction, therefore they gain it from the surroundings, which means heat goes down in those cases. The positive sign means energy is absorbed, it's drawn into the product, and it's taken from the surroundings, which means that the temperature goes down. So in this case, we need to put heat into our reaction in order for this to proceed. We need to take calcium carbonate, we could heat it, and then we end up getting calcium oxide and carbon dioxide driven off. If this proceeded without heating, then the temperature of the system would actually go down. This doesn't normally happen at room temperature. Usually you would have to put heat into it, but the heat you put in is absorbed by these products. Therefore, they have more energy, and in other cases, you would actually have the temperature going down because that energy is being absorbed. What you need to understand about thermochemistry and any chemistry, it happens in moles. We're doing the same sort of chemical equations that we did previously. Here's an example. Methane plus oxygen yields carbon dioxide and water. The heat of combustion, which means the heat that is released when this is burned, because you can tell this is a combustion reaction, is negative 802.2 kilojoules of energy. 1 mole, if I burn 1 mole of methane, it releases 802.2 kilojoules of energy. If I had half a mole, it would be 401.1 kilojoules of energy. It's the same mole relationships, just like 1 mole of methane to 2 moles of oxygen yields 1 mole of carbon dioxide. When you produce 802.2 kilojoules of energy, you make 2 moles of water. Again, this is exactly like I was talking about before. It's regular old stoichiometry. You're just dealing with a number representing energy as another part of this equation. Heat of reaction is the heat that is, so we're going to see a lot of different delta H's, I guess I should be saying. Heat that is released or absorbed in a chemical reaction is designated as a delta H for a reaction. We'll see quite a few different changes in heat, delta H values. In this particular case, this is the one we saw previously. This is a negative value when it's represented as delta H equals negative 393.5. But in this case, since it's now part of the equation, it's a positive number as a product. This heat is coming out of carbon and oxygen. If I were representing it as delta H of the reaction, the change in enthalpy of the reaction, like I said, this would be a negative number because it's coming out of the reaction. It's not going into the reaction. Now, we would also call this, in addition to heat of reaction, we call this heat of formation. It's heat that is either gained or lost when we're making a compound out of its representative elements. Any element, its heat of formation is 0 because that's always the starting point. In making any compound, you need to start with the elements. And in chemistry, we just have the elements. I mean, if you go into nuclear reactions, then you would be making the elements, you'd be making the atoms, but that's not a consideration in these particular sets of concepts. Now, in this case, this is heat of reaction because we're burning carbon. It's heat of combustion because you have carbon and carbon dioxide. It's also heat of formation, so there's 3 different concepts here. Heat of combustion is when we burn 1 mole of a substance. As we saw, we're burning methane, 802.2 kilojoules of energy is released. That, if we factor it into the equation, it's added in as a positive value on the right side. Now, what I know frustrates people is when we get into the understanding that these are heat of combustion is 1 mole of something burning. So in this particular case, if I needed to balance this reaction, this is not balanced, I would normally balance it with 2 moles of methanol to 3 moles of oxygen, 2 moles of CO2. That's the way I taught you to do it. Whole number values for each coefficient. However, heat of combustion would deal with 1 mole of methanol, which means I need to divide all of these values by 2. And therefore I would have methanol plus 3/2 of a mole of oxygen plus carbon dioxide plus water. I'm dividing all these in half because I need 1 mole of methanol for that particular case. And the heat of combustion for 1 mole of methanol will be 727 kilojoules of energy as a product because this is a negative value. It would be released, and we can burn ethanol for heat. We can burn methane for heat. We can burn lots of things for heat. The coal reaction we saw previously, that's also an example. We've been burning coal. In the whole industrial age, we were burning coal for energy as well. So back to where I was. Here's an example of a combustion reaction with the energy factored in. Good question. If 10.3 grams of methane are burned completely, how much heat should be produced? The energy is being released in this reaction. This is basically natural gas. This is a major component of natural gas. We're burning it. We're releasing energy. It's cleaner burning than the coal that I mentioned previously, although we are still making carbon dioxide as a product, which carbon dioxide levels are increasing in the atmosphere. That appears to be contributing to climate change as well as acidification of the oceans. So we start with what we know, just like stoichiometry. I have 10.3 grams of methane. I change it to moles, like I've always done. And I get 0.642 moles of methane because, again, I'm canceling out my grams and I'm keeping my moles, and that's how many moles of methane I have. Then, what am I looking for? I'm looking for energy. How much heat should be produced? That's my energy. So for 1 mole of methane, I'm making 802.2 kilojoules of energy. If I don't have 1 mole of methane, I have 0.642. It will be 0.642 times 802 kilojoules, my moles cancel out, and I end up getting 515 kilojoules of energy. Now, if I were to represent that as a delta H value, it would be negative 515 kilojoules because the heat is released from the methane. Few more terms we need to be able to be familiar with. Heat of fusion is a term just as a way of confusing sophomore chemistry students. It just means the heat that needs to be absorbed from a solid to a liquid at the melting point of that particular solid. The solid still has lower energy than the liquid. So the solid, like for water, ice at 0 degrees Celsius, the solid has less energy than the liquid at 0 degrees Celsius. So the liquid needs to absorb that heat in order to proceed. It would be the number of moles of whatever substance you have times the heat of fusion. No temperature change happens at the melting point until all of the solid turns into a liquid. Heat of solidification is the opposite of the heat of fusion. So heat has to be pulled out of a liquid such as water. Heat has to be pulled out of that liquid water in order to turn it to a solid, because those water molecules as a liquid are moving around, and you want to stop that movement. You have to pull energy out in order for that to happen. Same exact number. These are reciprocals. The heat of fusion, which is a positive value, it's an endothermic process. You have to put energy in to the compounds, is the opposite number of the heat of solidification. We have to pull the energy out. This is an exothermic process. You're pulling the heat out of water in order to make it ice. But the numbers are equal. It's the same exact number. When liquids absorb heat at their boiling points, they are vapors, they are gases. I prefer the word water vapor in the case of water as a gas. I don't like the word steam because I've always been taught that steam is when you see coming out of a boiling pot, that's the water, the vapor recondensing in little water droplets, which is why that's what the steam we see is. Some sources will use steam as the term for water vapor, but I always do prefer water vapor, just to be clear. And that directly relates to my molar heat of vaporization, which again, you need to put energy into the liquid. Water at 100 degrees Celsius, you need to put energy into it to break those hydrogen bonds that are keeping the water sticking together and turn them into a gas which has no attractive forces between the particles. Heat of condensation is the opposite. Heat of vaporization is an endothermic process. You're putting energy into the water in order to turn it into water vapor. You're pulling energy out of the water vapor and turning it into water with the heat of condensation. But again, these are reciprocal values. The heat of vaporization is equal to the negative value of the heat of condensation. We've seen specific heat before. This is our friend from way back when. Heat is abbreviated as Q, although since we're also seeing change in heat now, the Q value is delta H. We can write it that way as well. Delta H equals mass times specific heat times change in temperature. We know all of these things. Delta T is change in temperature. Let's not forget that. It doesn't mean the actual temperature. It means whether the temperature went up or down from a starting value. Here is what I was talking about in a concise graph. So what are we looking at here? We have water at negative 20 degrees Celsius, which is a solid. We heat up ice to the melting point. That's a specific heat problem with ice. Now, ice's specific heat is different than the specific heat of water, 2.06 joules per gram degree Celsius. I won't expect you to memorize this value. I would give it to you on a test. Then what happens? We're heating ice. We're putting energy into ice to turn it into water. Now we're dealing with kilojoules and we're dealing with moles. We're not dealing with joules and grams. So you have to be very careful. The energy that goes in for the heat of fusion is going to be different calculation than your specific heat. From there, once our ice at 0 degrees Celsius becomes water at 0 degrees Celsius, we're now into another specific heat problem where our change in temperature is 100 degrees. It went from 0 to 100. That's a good old specific heat problem again. Now, we have another example where we go across. This is heat of vaporization. This is water at 100 degrees Celsius. It's absorbing energy until it becomes water vapor at 100 degrees Celsius. And you notice it absorbs a lot of energy because it's very hard to break those hydrogen bonds and get water to not be attracted to other water molecules. And then from there, and notice down here also, 6.02 kilojoules per mole to turn ice into water, but 40.7 kilojoules per mole to turn liquid water into a gas. And then we get to leg E, which is, again, heating steam, which is another specific heat problem. Now, on the test that will be coming, you will have a problem like this. The amount of heat that must be removed for 245 grams of steam at 140 degrees Celsius to be converted into ice at negative 15 degrees Celsius. This is a 5-step problem, just like the graph. 1, 2, 3, 4, 5 different steps. So what do I need to know? In this case, you're taking water vapor. You're cooling it down from 140 degrees Celsius to 100 degrees Celsius. You're using your good old specific heat equation. We're doing this in joules and grams and degrees Celsius. So I end up getting 18,326 joules if I did my math correctly, which I can actually double check. So 245 times 1.87 times 40 is 18,326 joules. Okay, great. From there, that's the heat that would need to be removed from steam to lower it to 100 degrees Celsius. Now we calculate the amount of heat that must be removed for 245 grams of water. Oh, I'm sorry. I'm just reading the problem again. Okay. Next thing is I'm taking water at 100 degrees Celsius. Water vapor at 100 degrees Celsius. I'm removing the heat so it becomes liquid water at 100 degrees Celsius. And the delta H, for 1 mole of water, I have to remove 40.7 kilojoules in order to make that happen. I start with 245 grams of water, but I'm dealing with moles here, so I have to go grams to moles, and I get 13.6 moles of water. Which now, 13.6 moles times 40.7 kilojoules, because it's 40.7 kilojoules for 1 mole. My moles cancel out. I end up with 553 kilojoules. Next step is going to be cooling water down from 100 degrees Celsius to 0 degrees Celsius. I'm using specific heat again. So again, I plug in my numbers, and hopefully that is correct. I'll double check. So 245 times 4.18 is 1,024.1 times 100 is 102,410 joules. Okay. But again, remember, I'm dealing with joules, which we'll see very soon again. Now I have to take liquid water at 0 degrees Celsius and turn it into solid water at 0 degrees Celsius, also called ice. I have to remove 6.02 kilojoules from each mole of water to make this happen. Now, I did calculate moles earlier, but just to remind you, I do have, if I did want to do it again, I still have 13.6 moles of water. I'm assuming that no water is lost in this process, even though that's not entirely true. 13.6 moles, again, this is my heat of condensation in this case, and I get 81.9 kilojoules because my original is kilojoules per mole. Now, last thing, I'm cooling ice from 0 degrees to negative 15. Again, it's a specific heat problem. And if I did my math correctly, 245 times 2.06 times 15 is 7,570, approximately 7,571 joules. All right, we're good with that. So those are all my calculations so far. Cooling down water vapor, turning water vapor to water, cooling down water, removing the energy from liquid water, turn it to solid water, and then cooling down ice. I have to be careful with my units. I don't just add all of these up because I got joules and I got kilojoules. So I got to turn them all into kilojoules in order to make this work. Remember significant digits. I have really 7.57 kilojoules. Here I have 553 kilojoules. Based on precision, this is basically the same as 8 kilojoules. This is 102 kilojoules. You notice they kind of do all sort of more or less even out. But we can't have 18.326 kilojoules if I have 553 kilojoules in another case, or 82 kilojoules in another case. That's how much heat total, if I did the math right, that's how much heat had to be removed from my water vapor to bring it down to ice. One other change in heat is heat of solution. So with certain solutes, you dissolve them in water, for example, or another solvent, they can either heat up or they can cool down. These are your hot packs and your cold packs. You break that little package inside of the water and something dissolves, and if a hot pack, then it's an exothermic reaction. Heat is released, the water warms up. If it's a cold pack, the energy is absorbed by the solute and the temperature of the water goes down, and that's your cold pack. So sodium hydroxide is an example of an exothermic process when it dissolves in water, and ammonium nitrate is an example of an endothermic process when it dissolves in water. Now, sodium hydroxide also happens to be very caustic. It's corrosive. You don't want to put this in a hot pack. What they would generally put is something like calcium chloride, which also releases heat when it is mixed with water. But ammonium nitrate, even though it is explosive, can be found in standard heat packs. Of course, you would need a ridiculous number of heat packs in order to get enough ammonium hydroxide or ammonium nitrate to do anything, to cause any damage. Building an explosive, for example. You need a whole lot of cold packs to do that, and you'd probably get a call from the FBI for purchasing that many cold packs, because nobody would purchase them for any other reason than to be up to no good. So, when the solute, I think this is a repeat here. Yes, it is. Okay. So in this particular case, we're taking 100 grams of sodium hydroxide. We're dissolving it in water at 21 degrees Celsius, 1 liter of water. This is actually two separate problems. So first one is a heat problem. This is a good old thermochemistry problem. Sodium hydroxide has become sodium ions, hydroxide ions in water, and they're releasing heat. So I need to know how many moles of sodium hydroxide I have. 100 grams. I'm sorry, how many grams I have is 100 grams. I have to change that to moles. 2.5 moles of sodium hydroxide. How much energy is that? 44.5 kilojoules per mole of energy is released. So my moles cancel out. I end up with 111 kilojoules of energy. That energy came from the sodium hydroxide. It's being released into the water. So now we have a nice specific heat problem. My Q value is this much energy is being put into my water. I had to go from kilojoules to joules because our constant for specific heat is 4.18 joules per gram times degree Celsius. All right, so I put my joules in that equation. The other nice thing about water, 1 liter of water is 1,000 milliliters of water. 1,000 milliliters weighs 1,000 grams because 1 milliliter weighs 1 gram. I plug this in, I find my temperature change, which is 27 degrees Celsius. However, that is not my final temperature. That's how much the temperature changed. I started at 21 degrees Celsius, and I added 27 degrees, so the final temperature would be 48 degrees Celsius. That's not a huge amount of sodium hydroxide, which we're mixing into substantial amount of water, which is why when we mix sodium hydroxide, we have to be very careful. In fact, if you make a very concentrated sodium hydroxide solution, it can raise temperature to the point where you actually have the water boiling. And boiling water with a corrosive solute is not a good solution. So that's why they generally put the beaker in an ice bath, so you're not heating the water too much. Now, this is one of the monsters of all problems in first-year chemistry. The minimum volume of propane gas at STP that needs to be burned to turn 1 kilogram of ice at negative 20 degrees Celsius to water vapor at 150 degrees Celsius. This is climbing the mountain. This is everything we've learned so far this year, because this is stoichiometry with energy, with specific heat, with balanced equations, everything that we've done over the course of this year. That's why I love these problems, just to be clear. Of course, I need a lot of givens. I need to know, because I'm going to be heating up ice, I'm going to be heating up water, I'm going to be heating up steam, I'm going to be changing ice to water at 0 degrees Celsius, I'm going to be turning water to water vapor at 100 degrees Celsius. So I need a lot of constants in this, right? I need a lot of given values in order to make this work. Would you have to memorize these on a test? No. These are things you can look up quite easily if you needed to. So first, we will deal with energy. We're going to get the energy by burning propane gas. However, we need to find out how much energy we have first. So just like we've done before, I determine with specific heat, heating up the ice, using the specific heat value of ice, how much energy would I need to heat ice from negative 20 to 20 degrees Celsius. From negative 20 to 0 degrees Celsius, the temperature changes 20 degrees. From there, I melt that's a mistake. So this is a solid. I'm taking solid ice, turning it into liquid ice at 0 degrees Celsius. And my heat of fusion is 6.02 kilojoules per mole. That's 1,000 grams of water. I need to find out how many moles that is. 55.6 moles. Same thing like any other stoichiometry problem. Now I want to cancel out my moles and keep my kilojoules. 334.7 kilojoules of energy are required to take ice at 0 degrees Celsius to water at 0 degrees Celsius. This many moles, 55.6 moles of it. Next step is specific heat of water. I'm still heating this water now. Water from 0 to 100. Good old specific heat equation and good old specific heat answer given in joules. From there, I'm going, another mistake. So I'm going from liquid. You can tell I took my previous problems and flipped them around, but this is liquid water to gas water vapor. Remember, this is a very endothermic reaction. It needs to absorb a lot of heat. Liquid water has to absorb a lot of heat to overcome those hydrogen bonds. If I needed to, I'd turn my grams into moles again. I don't really need to do that, but what I do need to do is take the number of moles that I had, multiply it by my kilojoules of energy. It's treating this like a stoichiometry problem. This is how many kilojoules per mole, so 55.6 moles times 40.7 kilojoules, I get 2,263 kilojoules. And then I'm heating up water vapor with the specific heat of water vapor, just like we've been doing previously. So what I end up with are all of those values. Some of them are in joules, some of them are in kilojoules. I need to make sure that they agree. Add that up, and I need 3,149 kilojoules of energy in order to make this happen. Assuming that all of my propane burned perfectly, I would need to have a balanced equation for propane. Now, nice thing about propane, it doesn't require one of those funky equations where I have like 5 halves, because propane can be balanced with 1 mole of propane. I can balance this equation. The heat of combustion for propane, 2,221 kilojoules per mole of propane that's burned. A lot of energy in propane, that's why we use it in grills. Propane's also easy to compress into a liquid form under pressure, which is how we can put it in those tanks. From there, this is the energy I needed to make the water do what I wanted it to. And I'm canceling out my kilojoules because I want to find out how many moles of propane that would be. Turns out it's 1.418 moles of propane. And this question asks for volume of propane gas. So now I know how much energy I need, how much energy I would get from 1 mole of propane, therefore how many moles of propane I have, or I would need. Now I take those moles and I turn them into liters. So 31.8 liters of propane is the amount of gas at STP. We'll be getting to gas laws. These aren't always true at STP. We'll be getting to that very shortly. With that, that concludes our lessons on thermochemistry.